Good morning, everyone. You're welcome back. Please, can you check your time for me? I see it's your time to pass. Okay. Now, let's look at solution to assessment 3. Okay, so let's have a look at the first question. All right, the first question. So the question says, remember this is Factories 2023 November, question 2. A 10 kVA single-phase transformer for 2000 volts / 400 volts at no load has resistance and leakage reactance as follows. Primary winding 5.5 ohms and the reactance 12 ohms. Secondary winding resistance 0.2 ohms and reactance 0.45. Calculate or determine the approximate value of the secondary voltage at full load and the 0.8 power factor lagging when the primary supply voltage is 2000. Okay. So we look at that equation first. All right, so now let's check what is given to us. Apparent power, S is 10,000 volt amperes, that is 10 kVA. And the transformer is 2000/400 volts. Okay, at no load, it has resistance and reactance as follows. Okay, all right, so it has primary winding, okay, which is R1, is 5.5 ohms, and reactance X1 12 ohms, and the secondary winding resistance R2 0.2 ohms, and reactance X2 0.45 ohms. Determine the approximate value of the secondary voltage at full load and 0.8 power factor when the primary voltage is 2000. Determine V2 terminal, okay, at full load and power factor 0.8. Okay, so now what we do now is we just sketch the transformer. We're supposed to have like that. So we're given R1 5.5 plus X1 J12 R2 0.2 plus X2 J0.45. Okay. So now we are asked to calculate the secondary voltage, this V terminal, V2, the terminal voltage there. All right, at full load, when power factor 0.8. So when you have like this, we need to take all these impedances to the secondary side. All right. Now, in other words, so we should have like that. Sorry, you should take everything to that side. So this will be Z equivalent to. All right, if you take everything to this side, so that we have R1 prime, X1 prime, R2, X2. And we know that this total impedance, which is Z equivalent to, okay, is the same thing as saying Z1 prime plus Z2. Okay, so now we know our Z1, but I need to take this Z1 to this other side, right, which you can still write that as, I said, you are coming from this, coming from V1 to V2 all squared multiplied by Z1 then plus Z2. This will give you Z equivalent to. Okay, so let's check. Let's see what we don't have. We have V2, we have V1, we have Z1, we have Z2. So we're just going to write this like that. This is 400 V2 over 2000 all squared into Z1 is that 5.5 plus J12. Okay. Now 5.5 plus J12, just to make sure things are in order. 5.5 reactance is that, and then secondary winding 0.2, and this is that. Okay. Now we add that to this 0.2 plus J0.45. That is 0.2, then squared. This is like 0.04 into 5.5 plus J12 plus 0.2 plus J0.45. Okay. Now, you can multiply it, so you have just collect the like terms. This is 0.22, 0.2, that is 0.42 plus J0.48. Okay, so it's okay. Now let's see. I have to put this. Okay, so we have 0.42 plus, okay, so we have this to be 1.02 to an angle of 65.7. All right, so I think that's all about that. Now, this is that impedance. All right, so we got this impedance like that. So, and then I want to calculate V terminal if I know E2, right? V terminal will be E2 minus voltage drop here minus I2 Z equivalent 2, right? So the only thing we don't know is I2. We know that, which we have gotten as this. We know this, right, which is given to us as 400. We don't know I2. So let's get I2 first. I2 is S over V2, right, which is 10,000 divided by 400. So this you get 25. Right? Then we can now substitute that V terminal is E2 400 minus I2. But remember that this I2 is set at full load with a power factor of 0.8, which means at 0.8 power factor, and this is 0.8 power factor, all right? So, which is arc cos, to get the angle, arc cos of 0.8, that gives about 36.87, okay, 36.87. So this will be 25 with an angle of minus 36.87, because that was lagging, right? Yeah, it's a lagging power factor. So this is lagging, all right? So that's I have to put minus. So I'm going to write, so I'm going to substitute here, 400 minus 25 with an angle of 0.87 multiplied by Z equivalent to, which is this, 1.02 with an angle of 65 point that. Okay. So I just want to get this first. So this will give you 25.28 25.5 at an angle of 28.83, 400 minus that, okay? 25.5 with an angle of that. So let's see. So you get 377.86 with an angle of minus 1.865. Okay, wow. Did you get that? So you're going to have 377.86 with an angle of minus 1.865 volts. All right, so now the question says, draw a typical installation of a pole-mounted transformer to supply 400 volts to rural consumer for 11 kV spare line. Okay, this is actually a repeat of November 2004, question 2.2. And the question is also covered in our electrical reticulation course. All right, so now, so we're asked to draw the installation of a pole-mounted transformer to supply 400 volts to a rural consumer for 11 kV spare line or spare network. Now, when we talk about a spare network, we're saying you can have like, if these are poles, these are electric poles, right? Now, which is linear, all right? Now you can tap power from here, maybe put a transformer and supply the consumer. So we call it a spare network. It's like a T, all right? But now, the way we start it, if you want to sketch, let's just put up a single line diagram like this. So I'm going to have a line first, all right? Then for the line, let's say there's a fuse, you can just sketch like that and say this is a fuse, all right? And then from the fuse, you are going to have an isolator, okay? But this isolator is actually like a gang isolator, all right? So this is isolator, all right? Isolator switch, so fuse, isolator switch, and then before you come to your transformer, right? And here you can now distribute to your load. And because it's pole mounted, there ought to be a surge arrestor, all right? So we can just put a surge arrestor. And this arrestor must be earth. Okay? Okay, so this is a surge arrestor. This is a fuse, that's a switch, isolator switch, or sometimes we call it gang isolator, like that is gang operating switch. Okay, now, so I'm going to, this is just like a single line diagram. But what they said was draw the typical installation. So I'm going to look at this and draw, all right? So we have, let's have a H pole. This is our H pole. Okay, and that's the support. Okay, like that. Now, let's put another support here. Remember that you cannot just connect this like that as it is. There must be a support, an insulator, a disc insulator. In fact, let me just bend a little bit and so that you see what I'm saying like that. This might just be an insulator. Just to see, okay, an insulator. Okay, so it's like that. So insulator, they are used to support the conductors. Now, I'm going to put this surge arrestor there. Can push surge arrestor, and then the lines, these lines that comes like that, can come to there. And these surge arrestors This has to be grounded. So there's going to be a wire which needs to go to ground. They have to be grounded. The essence of a surge arrestor is in case if there's a lightning striking this, we want this to intercept that to the ground. All right. So now I have this support 1, 2, 3, just to support the cables. Now I'm going to put my fuse. So from here, you have a fuse. Okay, like that. And then for the fuse, you have an isolator. But this isolator is a gang isolator. So there's going to be a support for it with a connection, which I can come down here. This is the ground. Let me bring this to this side. There should be an operating stick, operating handle, all right? So here we have an operating handle. If you pull it like this will open. This. So I can just have like that. Okay? Just put them. All right, and then after that it comes to the transformer. The transformer should be mounted, okay, on a platform. So you have this transformer mounted, right, with their respective 3-phase bushings. So I need to take this wire there to this bushing, that to that, and that to that. Okay? And it's mounted on this platform. All right. Okay. So that's our transformer. And then now on the output of it, the secondary side of it, we need to get out that wire of the secondary. Now you want to feed people, so you can either connect it to a load distribution board. From the board, then you can now disseminate. But I can have times you can have this goes into a board, okay, distribution, LT distribution board. Let me put it here, low tension distribution board. Okay, and then from here you can now run your wires. Maybe it depends on the configuration. So I can actually have some what do you call it now? Insulators like that, where wires from this DB board can go in there, phase A, phase B, and then you can now run out the low voltage line, the LT line. You can even tap also from here, maybe on this other side, here, all right, that is phase A, phase B, phase C, all through there, into this. Yeah, just to have this section, and then you have that section, so you can now reticulate downstream. Okay, so let's name the parts. This, what you have here, is isolator. Remember, we have the normal disc insulators that are used to support these conductors. These are disc insulator. Okay. Now I have here fuses, 1, 2, 3 fuses. Okay, but since I can just say fuse, but these are 3 of them, and then gang switch. So it's GOS, or you can just call it isolator. Okay, that's isolator, but it's a gang because this is the operating handle. When you pull it this way, it will open. Okay, so that is here is operating handle. All right, for the isolators, so you can just turn the ground and pull it. Then this will open. All right. So this is a 400 volts line. If this is going also this way, 400 volts line. All right. Did you get that? Check your time. What time is it now? See, it's your time to pass, right? So when you do this, you get some mark. All right. So this is lightning arrestors are very important, so that it will prevent this from any impact due to lightning. Okay. So that is a schematic. This is a layout, the one that we say we must sketch this. So it's just a schematic diagram, schematic. And this is. So when you do that, you get 6 marks. All right, so let's look at that question. Now, you are asked to describe, let's see, the question says we must describe and clearly distinguish between touch and step potential in relation to electrical earth. Describe. Okay? So, and distinguish. So they want you to sketch also. When I talk about describe and distinguish, now, we don't just say a touch voltage is this or step voltage is that, you must describe it, all right? So if, for instance, you have, let's say, a lightning mast, let's say you have a mast or any kind of equipment or a pole, all right? And then, there is, what is it called, lightning. If lightning strikes that, okay, or a live wire touches this. Remember, this is conductive. This is a structure. Let me just put like that. Let's say you have, what I put it? You have, this is a support. A support to electric cable conductor. And this happens to touch that. So if a live wire touches this, then current is going to flow to the ground. And then when it flows to the ground, this is a fault. Live wire touching that. So as it flows to the ground, now it's going to flow from here to a remote area. So if current is going to flow from this point to a remote area, it means that at this point, the potential is higher than any other remote area. Okay? So in other words, if I know the potential at this point, and at that point, at that point, at that point, as you go further away from this, the potential decreases. So let's say you have, just to represent this as a potential difference between one point and the other. Now, if someone happens to stand here like that, when this live wire touches that, or when a lightning strikes this. So lightning strikes this pole, current flows to the ground, and someone is here standing and is touching this. Now, what happens is this. The first thing is that as current is flowing down, the current has to decide, on coming to this point, the current should decide whether to continue to flow through here, out, or continue like that, out. And then also whether it should continue to flow like this, through this leg, through that, out, or flow this way, depending on the impedance of that. So even if someone is also standing here, and there's a potential difference between this leg and that leg, so the current as it flows has to decide, should I continue to flow this way or to flow through there like that? Okay? So now we start with the first definition, a touch voltage. So as this guy is touching this, there's a voltage difference between the point he's touching and the earth, because this is earth. All right? So now the current coming down here will decide, can I continue like this or can I go this way? This voltage difference is what we call V touch. All right? Now, do you know that in a substation, if you go to a substation, you have stones, or those small white stones or rocks that you put in a substation. That stones are not meant for to decorate the substation. It's actually just we put it there to increase the resistance of this particular person with respect to ground, so that if I have stones like that, it's like I have added resistance, so that if I can calculate the resistance of this hand and that, this might be 5 kilo ohms, 1 ohm, 1 ohm, 1 ohm, maybe 5.3 kilo ohms. But from here to here, the resistance is very small, so the current will rather flow through here than going through this guy. Okay? So now, this is what we call touch voltage. So that means V touch, which is your touch voltage, because they say we must clearly describe. So now this is the difference in potential between the surface potential, which is this, and the potential at earth equipment that a man or someone is standing and touching. So the potential difference between this point is standing and touching, and this is your touch voltage. Okay? So let's write it. Say that this is the potential difference. So it's a potential difference between the surface potential, that is between this is our surface. So our surface between, let's say, Earth's surface potential and potential, that is this point, potential at Earth Remember that this is grounded, it's earth, okay? So at earth equipment, while, how do I put while, okay? So while a man is standing and touching the earth structure, and okay, so the potential difference between this surface where the man is standing and where the man is touching. So that is touch voltage. Okay, and again, so when that current is flowing down, or a lightning current flowing down to the ground, now as it flows away, now when it comes here, it has to decide, should I continue this way or should I go like that? If the impedance within here, maybe the resistance of the earth or resistivity is very high, okay, so the current will say, no, let me go through this leg, because the leg has a path of low resistance, can go through here than going through there. All right. Now that voltage difference between this leg and that leg is V step. Okay, that's a step voltage. V step voltage. So now this is a potential difference that is developed when a man bridges a potential difference that is developed when this man is bridging, where he bridges a distance, just a distance of 1 meter, bridges a distance of, which is between the two legs, of 1 meter with his feet. Okay, while not touching any other earth equipment. Okay, so now, so that's a distance, that's a voltage between this leg, or like that, between these two legs. Do you know this is the reason why when in the farm, when there's lightning, when lightning strikes, like let's say a tree or a structure, then you will see the animals, they just die sometimes. It doesn't mean that the lightning did not strike the animal direct. Okay, the animal, this is a tree or a structure. Lightning struck that structure, and this is an animal. If I know how to sketch. Okay, so as this current flows into the ground, when it's come here, to decide, should I continue to flow like this, or can I go through this? Then you see the animal will just die. All right, so now the essence of putting stones in a substation is actually to insulate this person from the impact of step potential. So that if current is going to flow like that, it has to decide, can I go through here or continue? It cannot go through here because I have put a very high resistance or resistive component, which is just small stones that you put in a substation. All right? Okay. Did you get that? What time is it now? Check your time for me. All right. Okay. So now let's look at this question. Now the question says two 250 kVA transformers supplying the network are connected in parallel on both primary and secondary sides. The voltage ratios are the same. The resistance drops are 1.5% and 0.9%, and their reactance drops are 3.33% and 4% respectively. Calculate the loading, the kVA loading of each transformer and its power factor when the total load on the transformer is 500 kVA at 0.707 power factor lagging. Then question number 2, two 5 MVA transformers are placed in a transformer yard close to a coal handling plant, and form part of the substation that feeds the coal handling plant. Draw up a maintenance schedule for the transformer. All right, so let's look at the first question. So we got two transformers. Which are connected in parallel to feed a load. Okay? And each one is 250 kVA, 250 kVA. And we have the voltage ratios, their resistances and reactances. Resistance 1.5%, 1.5%, and reactance is, let me just put like that, just the impedance. And this other one is 0.9%. And then their reactances are 3.33%. And this is 4%. Okay. Now, we are also calculating the kVA loading of each transformer and its power factor when the load on the transformer is 500 kVA. So this load is 500 kVA at a power factor of 0.707. Okay. So we want to see the loadings. We want to see the contribution of that and that, okay, into this. All right, I want to see their contributions. So the SA and the SB. Okay, so I want to see the contribution SA, contribution SB. All right. So we know that the contribution of the loadings of this towards that, the supply of this to that, which is the contribution of this to that total load, is S of the load multiplied by, we take the impedance of this one, this is B, Z of B over ZA plus ZB. So the same thing, S of B is S of load multiplied by ZA over ZA plus ZB. All right, so you may not need to worry yourself, dividing or whatever. You can just use these values as they are, because if I take this by that, it will still give you the same, even when you have put this as 0.015. Okay, if you divide up by 100, you still get the same thing. So what I'm saying, you can just leave this as it is, all right? So let's just get ZA. ZA is 1.5 plus J 3.3, all right? And ZB is 0.9 plus J 4. So all in percentage. Now ZA plus ZB will give you add them together. This is 2.4 plus J 7.3. Okay. this is 33. So this is 1.533. Of which you can just check with me. You can convert all this to polar form. Just check it with me if you got ZA in polar form to be about 3.652 with an angle of 65.75. Okay, so you can also check Z of B will give you about 4.1 with its own angle of 77.32. And even ZA plus ZB, which is 2.4 plus J 7.33, you just check if you got the same as 7.713 with its own angle of 71.87. So once you have that, we're going to substitute this here. Okay, but you must check, make sure that you get the power factor of this, the angle of that. Theta is arc cos of 0.707, which is 45. But this is lagging, so it means that this is 500 with an angle of minus 45 degrees as our S load. So you have this, we have all these parameters. Let's just substitute in this equation 1 and equation 2. All right, so that SA will now be ZB, which is 4.1 with an angle of 77.32 over ZA plus ZB, which is 7.713, an angle of 71.87 times S load, which is 500, an angle of minus 45. Okay. So just check this with your calculator and see if you can get the same thing with me as 265. 265. That's a 265.785 with its own angle of minus 39.5 or 0.56. All right. Then you do the same thing, SB. So we have SB, which is that is ZA, and ZA is 3.652, triangle of 65.75. Okay. Then divide by 7.713 with an angle of 71.87. Right, then you multiply it with that times 500 with an angle of minus 45. Okay. So check if you can get 236.743. Then with the angle of 51. Minus 51. 0.129. So this is in kVA, kVA, kVA. So power factor for this, because they say we must calculate power factor, so which is cosine of 51.129. All right, if you check that, you will get about 0.628. You can also look for power factor of that, 39.56. Okay, that you get about 0.77. This is minus here, so you must put lagging. Lagging. The same thing here is minus, you must put lagging. So if you are asked to comment on these answers, you can see that this, remember this is rated 250, but you can see it's delivering 265. Okay, this is rated 250, but it's delivering 236. Can you see what the impedance of the transformer can do? Because of this impedance of that, you can see it's a little bit overloaded. Check your time. All right, you must check your time for me. All right, so now let's look at the next question. So the question says, two 5 MVA transformers are placed in a transformer yard close to a coal handling plant, and they form part of a substation that feeds the coal handling plant. Draw up a maintenance schedule for the transformer. So, look, these are two transformers, 5 MVA, and they are in a coal handling plant. Near a coal handling plant, there is issue of hazard. Coal is also explosive, and with the dust of coal, it can accumulate even on the parts of these transformers. It's a whole lot of things that need to be checked. So what I'm going to do is, let me just display this here to make it faster. Look at it. So the maintenance schedule for each transformer, given the frequency of inspection and the checks to be made on each occasion, will be laid by the colliery electrical engineer, and this must be followed closely. Okay, so now the maintenance schedule that we have to look at. Okay, number one, there should be a regular inspection. You need to check for signs of corrosion, loose connections, because if there's any loose connection, remember the area is explosive, so we don't want loose connection. We must check any physical damage. So regular inspections will help identify issues earlier. Then temperature monitoring. We have to monitor the temperature. Transformer generates heat during operation. So monitoring the temperature ensures safe operation. And if you have a dry type transformers, in particular, they require temperature checks. That's why you have to put, you have to embed a temperature sensor, a sensor to check the temperature of this equipment or this transformer. So you just need to go to the transformer temperature gauge, all right, and check and make sure that this transformer is not heated up. Now, cleaning. Remember, this is it's a cool area, so cleaning and dust removal. You must keep the transformers and its surroundings clean to prevent dust buildup, which can affect performance. All right. And then testing and diagnostics. There should be a periodic testing which will ensure that the transformer is functioning correctly. Insulation resistance tests, oil quality checks, for oil field transformers, and the other diagnostics. They are very important. Now, protection system maintenance. You have to ensure that the protective devices, such as relays and fuses, are functional and calibrated correctly. Then oil field transformers. So if your mine uses oil field transformers, so regular oil sampling and analysis are crucial to assess insulation conditions and detect any issue. Okay, did you get that? All right, so that's all about that. Now let's look at the next question. Let's look at the next question. This is actually Factories May 2021 question 8.1. It says a centrifugal pump in an on-ground chamber of a high security facility delivers 550 liters per second through a vertical column against a static head of 400 meters, and it needs 330 kilowatt to drive it. A leak of 25 liters per second develops exactly halfway up the delivery column. As a result, the quantity delivered at the top of the column drops to 29 liters per second. Friction head loss in the delivery column is 0.005 Q squared meter per 100 meter, where Q is a flow in liters per second. Calculate the power required to drive the pump under the new conditions if the efficiency remains constant. Did you get that question? All right, so let's look at the solution to this question. Okay, so let's say we just have something that looks like this. Our pump is here, and our static head is 400 meters, and the power into the out of the pump is 330 kilowatts. All right, and Q is 50 liters per second. All right. Now, later there was a leak. I'll just have the same pump. Then there's a leak somewhere. So a leak of 25 liters per second developed exactly half up the column. So 25 liters per second developed half, about 200 meters of the column. As a result of the quantity delivered at the top of the column dropped to 29. So here, 29 liters per second. And then frictional head loss. This is where the problem is, okay? Frictional head loss in the delivery is, this is where you need to get it very well. Why some people failed the question. frictional head loss is 0.005 Q squared meter, but this is per 100 meter. Okay. Calculate the power required to drive the pump under the new condition. Power under new condition. Okay. So this is actually where the problem is, that. And if you check what we did last time, we just want to calculate if I can get rho G H Q, and I'll get my power. All right. So, but here I'm just going to get the power to derive to move this and that from here up to this point to get rho G H1 Q1, and I'll add it with the power to drive to move the remaining liquid, that is 29, from here to here. Rho G H2 Q2. So here is Q1. Q1 is 25 plus 29. Okay. Q1 is 25 and 29. So have, and let me just make sure that it's also against the static head of 400 meters. Okay. So have 25 plus 29, that's 54. 54. Okay. Now, and Q, that's Q1, and Q2 is 25 liters per second. So we are just solving this. This is what is required to pump the whole of that through that against this 400 meters height. Okay. Now, but if you check the equation now, it says a leak of 25 liters is developed, exactly half up the delivery column. Now, as a result, the quantity delivered at the top of the column dropped to 29. So, frictional head loss is given to you. Calculate the power required to drive the pump under the new condition if the efficiency remains constant. So now, you see here, they said here the efficiency remains constant. I don't even know, do you know that if I have the whole of this, look, I can even use this and that to check whether this is okay, because this thing needs 330 kilowatt. So I need to use this to get the efficiency of this pump. Now after that, I'll come here and I'll use that efficiency here, because the efficiency of the pump. All right. So let's get this one first before we come here. Let's just get our power. Now, if you check, we have a static head, we have frictional head. H frictional is 0.005 Q squared, and this is per 100 meters. So, and this is 400. So I need to multiply that by 400 by 4. I just want to get make sure the Q is in meter per second. Good. So I'm just going to multiply this by 0.005 by 50. Can I just solve this in here so that you know what I'm saying? So I have H friction 0.005 by 50 squared. Now this 50 squared like that, this is per 100 kilometer. Is different from the one we solved last week, the way it is asked. Okay, so for each 100, the frictional head loss is 0.005 Q squared. Okay, each 100. So how many hundreds you have here? 4. So you must multiply that by 4. This is just the only thing that what made people to fail it. Okay. All right. So now let's get that. I just want to get the power to push this up, and I'll use that to get efficiency here because I'm going to use it on this system. So I have 0.005, let's say 50 squared times 0.005 times 4. Okay, which will give you 50 meters. All right. Then, so the total head will be the static head plus the frictional head. Head static plus frictional head. So which will give you 400 plus 50, that is 450. Okay. Did you get that? So what again? I think that's all. Now we can easily now calculate. There's something closing there. So we can easily okay. So we can easily calculate our power. Now, this is water we are pumping, right? It's water. We are pumping water, right? Underground chamber of that. Okay, so I'm pumping water. So I have 1,000 times 9.81 times what is it? The total head 450 times that 50. Now 50 liters. I must convert this one in this 50 liters per seconds. You know, 1,000 liters is 1 meter cube. So 50 will be divided by 1,000. Okay. So I'll have 50 times 450 times 9.81. So I'll have 220,725 watts. Okay. Now, what will be the efficiency? Look, this is now, sorry, this is power, what is required is P in, is 330, right? 330 kilowatt. Where is it? Yeah, 330 kilowatt. All right, so that means that the efficiency, pump efficiency, is 220.725 in kilowatt divided by 330. 0.669. 0.67. Okay, that is that pump's efficiency. Let's assume that let's say if you made a mistake and you did not multiply this by 4. Okay, so you are going to get something smaller also. All right, so which will be different from that. All right, so now we have pump efficiency. Now the question says, calculate the power required to drive the pump under the new condition if efficiency remains the same. Okay, this is our new condition. Efficiency still remains 0.67. All right, so let's check the power to move from here to here plus power to move the remaining liquid 29 from here to there. All right, so let's have a look. Now, in that case, our Q1 is 54 liter per second. All right, and our Q2 is 25 liter per second. Q1 is from here to here. Now Q2 is from here to here, from here to there, 29. Q2, 29. Just to pump the remaining, this 29 from here to there. All right. So let's calculate H1. So H1 is the same thing as what H static plus H friction. What's the static from here to here, which is 200. So 200 plus H friction, and H friction is this per 100 meter. So we'll have 0.005 by Q squared, that's the Q2 squared, Q1 squared, 54 squared, and it's per 100. And this is two of them, 200, which is twice, times 2. Okay, so we'll get 0.005, or let's say 54 squared, 54 squared times 2 times 0.005. 29, okay, 29 point something plus 200, so 229.16, okay, meters. Now, so that means I got this, and let's look for H2. H2, which is now from here to here. So it becomes H static 2 plus HF2, which is the static from here to here is still 200. So 200 plus now 0.005 by that liters from here to here is 29 liters, 29 squared, times is 200, which is twice because it's per 100, times 2. So we have 0.005, or let's say 29 squared, 29 squared okay, times 0.005 times 2. So you have 208.41. 208.41, okay? 208, because it's 8.41, okay? Now, that is our H2. So we got H2, we know Q2, we know efficiency, so that means the power, remember that this and that, this and this are the same. So it's going to be 1,000 times 9.81 into H1 to 9.16 H1 Q1 Q1 is 54. Remember that if 54 you divide by 1,000 to get 0.054. This is the meter cube per second. And plus H2 is 208.41 multiply Q2, and Q2 is that 29, 0.029123, okay, like that. All right, so let's get from that side 208. Okay, remember that we must divide by efficiency of 0.67. Got 269.68 kilowatt. All right, so now let's have a look at this question. Now this is Factories June 2011, question 8. The data shown below is derived from a constant speed test of a centrifugal pump. Q in liter per minute is given. The manometric head 18, 17.55, 16.5, okay, and the rest at a different flow. And we're given the efficiency, and the pipe friction is given as Q squared over 700,000. The static head against which the three pumps are to be used in parallel is 12 meters. Now we have to calculate the quantity pumped and the power demand when the following number of pumps are run at the same time. Okay. All right. Did you get that question? What time is it now? Check your time. All right. Now what we do is let's just sketch that table first before we continue. Before we go on, so we have Q, which is in liter per minute, and we got HM, metric head, and then we got efficiency. This is pump characteristics, okay? We can plot that curve, 0 efficiency, and this is 200, this is 17.55, and this is 48. It's 400, 600, 800, 1,000. Okay, let's look at their respective head, 16.5. So now, you can use this to plot the pump characteristics, okay, which should look like that. Right, before you even talk about where you are going to install the pump, okay, which is a system itself, system characteristics. So now, okay, so we have that, and then the static head. The pump is going to be installed somewhere where the head, the height for the pump to ground is about 12 meters. So static head, let me write this here. H static is 12 meters. And then the friction head, HF, is Q squared over 700,000. Okay, so you can use this. Remember, we are saying this is the pump characteristics, but now this is the system. This is where you are going to. It's like you have a height like that where you put a pump there. Okay, and this height is about 12 meters. And then there are going to be some losses as the water flows through the pump. Now, or the static will be the pump is here and the pump is going to pump something up like that, about 12 meters. And through the pump, there are going to be some losses. Okay, so you can use the head loss, the static head plus frictional head to get the total head. Then we use that to plot the system characteristics and mesh that system characteristics with the pump characteristics. From there, we'll be able to calculate the quantity of, from the operating point, get a quantity of water that will be pumped. When you have one pump, you have two pumps. Okay? So, let me just write this here. So HS is 12 meters, and the HF is Q squared over 700,000. All right. So now, let's first of all plot the graph of just this and see how it will look like. And then after that, we plot the graph for two pumps, and then that of three pumps. Okay, let's just see how it will look like first, okay? Let's see. Just want something like this. So I want to use this side. What can I use here? Okay, I'm still going to do something here. So I just want to plot the characteristics of this pump first, all right? Just to see how it would look like. The head maximum is 18. right? So I can divide this into 18, like 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. All right. So, and then flow is 0 to 100 up to 1,000. So I can even say 100, 200, 300 like that. Okay, get up to 1,000. Let's say 100, 200. All right, you see, the reason why I have to give enough space is because by the time you have two pumps, okay, two pumps in parallel, now the flow is going to double, right? So you have a space for double, and then when you have three of them in parallel, the flow will be tripled, right? So now, so let's I have this, okay. Let's see. Let's just plot the graph. This is even also, okay, I'll come to efficiency. Let's plot 0 and 18. This is head, this is flow. So 0, 0 flow, 18 head. So we have this 200 flow and the 17.55. So 200, this is 17, 18, 17.55 will be somewhere there. And this is 200 flow, like that. And the next one is 400 flow, 16.5. 400 flow, 16.5. Then we'll have 600 flow, 14.5. 600 flow, let's do like this, 14.5. And then 800 flow, 11.5. 800 flow, 11.5. 1,000 flow, 5.5. 1,000 flow, 5.5. Okay, so for now, this is the characteristic curve of the pump. Okay, that is this pump characteristic curve. If you want to plot also the efficiency of that pump, efficiency, so efficiency starts from 0, maximum is about 77, so I can just take it like 10, 20 up to 80. So let's say here is 0, let's say here is 10, 20, 30, 40, 50, 60, 70, 80. Okay, so that if I want to plot efficiency, I have efficiency is at a head, at a flow of 0, efficiency is 0. At a flow of 0, efficiency is 0, you get that. At a flow of 200, efficiency is 48. At a flow of 200, efficiency is 40, 41, 42, 43, 44, 45, 46, 47, 48, maybe somewhere there. 200, this is 48. At a flow of 400, efficiency is 68. At a flow of 400, efficiency is 68, 65, 6, 7, 8. At a flow of 600, efficiency is 77, 600, efficiency is 77, 70, 75, 77, maybe somewhere there. Then at a flow of 800, efficiency is 72, 800, efficiency is 70, 71 to somewhere there. And efficient at a flow of 1,000, efficiency is 50. For 1,000, efficiency is 50. For 1,000. Okay, so you need to now use something, okay, to, where is it? What can I use now? Just checking what can, a nice curve. Okay, just want to make a curve. Let me just use my hand. That is a curve that we curve like that. And go through here. Okay, that's the efficiency curve. All right. So now, this is pump's characteristics, which is an efficiency. All right. Now we're going to now mount this pump, subject it to this head. All right, so I will be able to sketch the system characteristics and see where these pump characteristics will mesh the system characteristics. From there, we'll be able to get the operating point. Okay? So now, let's start. Now we have head here, total head for the system now is 12 plus Q squared over 700,000. All right. So in other words, we can easily calculate that head. I'm going to put the head. This is now for our system. This is for pump. This is for our system. All right. So we're going to use, so we'll be using that equation just to derive the pump head, the total, the system head. So now, if I put I'm putting 12 plus q squared over 700,000. So here, right, if I put q as 0, this becomes 0, so you'll be left with 12. Right? So you come here, you put q as 200. 200 squared divided by 700,000 plus 12. You get 12.057. 12.057, which is like 12.06. Okay. Do the same thing with that 400 squared. Divide 700,000 plus 12. Get 12.23. Okay. I have 600 squared. Divide 700,000 plus 12. 12.51. 514. I can just take as 51. 800 squared divided by 700,000 plus 12. 12.91. Okay. Then we'll have 1,000 squared divided by 700,000 plus 12, about 13.43. Okay, so this is just for one pump. I mean, this is just the head, right? If I want to just look at this system, compare it with this pump characteristics, right? Just one pump. We can plot that graph for it, just to get operating point. So in this case, the system characteristics, when flow is 0, this is 12. So when flow is 0, the head is 12. So the system starts here. Okay, system characteristics. When this is 200, the head is 12.06. 200, the head is 12. 12.06 is almost like 12, huh? Because it's almost like that. 12.06, it's almost 12. Okay. When this is 400, this is 12.23. 400, 12.23. It's just increasing a little bit. When this is 600, this is 12.5. 600, it goes to half of this, 12.5. When this is 800, it goes to 12.9. 12.9 is almost 13, but just say 12.9 somewhere there. When this is 1,000, this goes to 13.4. 1,000 This is 13, almost 13.5 by 13.4, so I take that to this. So you will see that the characteristics curve, the system characteristics will look like this. Now, I don't know, you see, I don't know what is going up, but I'm going to stop here for now. All right? If for this one pump, we look at the intersection of the pump characteristics and the system characteristics. This is the intersection. Okay? All right, so now that is the intersection. If you can go down here, whatever you get here becomes the flow, because the question is to calculate the quantity of water being pumped. So this point is where you're going to get what is being pumped. All right? So in other words, for one pump, just for one pump only, all right, what will be Q? Q for that one pump will be, for me to get this, I need to trace this down. That is 700 something. So you trace it down, you can get about, if you use this, you will get, let's say 710, okay, 710, Q is 710. But remember that this is liter per minute. Okay, you can also calculate, get the head. This is the operating head. You trace this like that, okay, to get operating head. If you trace this, you are going to get about 12.7 operating head. Okay, that is your head 1. Will be 12.7 meters. If you want to check efficiency, you see this point where this intersects, you can just move up to see where it intersects the efficiency curve. All right? So if I move this up here, this is where it intersects efficiency curve, and you trace it back to efficiency. This efficiency here is about 75. So let's say 75. Okay, if you use your graph, you'll be getting about 75.5. Okay, efficiency for one pump, 75.5. Now, just for one pump, we can now calculate the power, because the question is to calculate the quantity pumped, okay, which we have calculated, that is Q, and the power demand when the following number of pumps are running at the same time. For now, we're looking at one pump, okay? So this is the head, and this is efficiency, and this is what is being pumped. Because they said calculate the quantity pumped. All right, so quantity pumped is that 710 liter per minute, which is the same thing as, you can divide by 1,000 to make it in meter cube over 60 to make it in seconds. So it will be 710 over 1,000, 60, all right? Just to put it in meter cube per second, so you have 0.0118. This is meter cube per second. Now, you can therefore calculate the power, all right? The power is rho G HQ, okay, over efficiency. So we're looking at, just for one pump, rho is, I hope this is water, right? We're pumping water. A centrifugal pump. Now we're pumping water, so 1000 times 9.81 times the head, okay, which is 12.7 times the flow, this 0.01183, divided by efficiency. Efficiency, this is percent, so 0.755. Divide 0.75. So 1,952.68. 1,952.68. This is in watts, which is 1.95 kilowatt. Okay, so that is for one pump. Now we are going to look at two pumps. Okay, that is the second one, number 1.2. Now, this place is going to be a problem. Okay, so for the second pump, for two pumps, just thinking of how, okay, let me just put like this. Two pumps. For two pumps, what will be the flow? The flow, remember that when you have two pumps in parallel, pump 1, pump 2, and in parallel, so you have Q of this one and Q of these two all together in. So here will be Q1 plus Q2. Okay, when you have them in parallel, just like resistors in parallel, all right? The current will add up. So here, the flow will add up. So in other words, we are going to plot the flow for two pumps. See what we are going to get. Flow, double of this for two pumps, 0. Double of that, 400. Well, this is flow for one pump. Flow for two pumps, you just double all the flows. That will be 800, 1,200, 1,600, 2,000. See, flow is even getting up to 2,000. So see this flow, I stopped here. I need to move flow even up to 2,000. All right. This is 900, 1,000, 1,100, 1,200, 1,300, 1,400, 1,500, 1,600, 1,700, 1,800, like that. Okay. So let's plot this graph, right, and see, just to see what we can get. Okay. So let's remember when we wanted to plot the first graph for the pump is head against flow. So the head still remains the same against this flow. All right. So it means that for pump 2, you have any, okay. Let's look at pump 2. Pump 2, you have head against flow. When flow is 0, the head still remains 18. Okay. When flow is 400, the head is 17.5. So where you have 17.5 here, that is where you have a flow of that. Okay. Where you have the 16.5, this 16.5, the flow is 800. That's where you have 800. This 800, and the flow is 16.5. Okay. And then when you had 14.5 head here, the flow is already 1,200. So this, you just extend it until you get to that 1,200. So here, when the head is 11.5, this is 11, this head is 11.5 here, okay. The flow is 1,600. The flow is 1,600. When we had 5.5 head, which is here, 5.5 head, this one, you keep on going to a flow of 2,000. Flow of, so it's just going to 2,000 somewhere, all right? So, but you plot this. Okay, that is for pump 2. Now, in this pump 2, we are going to calculate the Q, right? Just to trace Q. So we are going to trace Q, and we trace the H. So Q is actually where this curve, the system curve, intercepts this. You see now, we stopped here for that curve, but you see this curve is still going. If I have more flow, at least this can go up a little bit so I can cut across this. So what I will do is, let me just say 1,000, you can use it to 200. Let's see 1,200, just to see where this place we pass through, and also 1,400. Just want to see what we get there. Okay. So now, so this static head. Okay, so this is for static head, right? So I want to see this. I want to see how the static head will look like. Okay, I just want to extend this, all right? I want to see what will be the static head here. The total head here, which is static plus friction head. Let me just, I want to make sure it cuts across here. So let's say 1,600 or so. Okay, just want to get that. So that I can complete this to go wherever it wants to go. just to cut this. All right, so from there I'll be able to get my operating point. So I'm just looking at this. Just want to check that. All right. So at this place, that system, this is our system curve. Okay, I want to extend the system curve. The system for a 1,200 is 12 plus 1,200 squared over 700,000. Just want to check how much that will give us. 14.057. Okay, at least 14.057 is somewhere, so it's going. Okay, by the time I get with the flow of 1,200, I'll get this up to a point. So I want it to cross here. So let's look for 1,400. 14.8. 14.8, at least 14.8 is coming, which is going to be somewhere. Okay, it will cross it. Let's look at 1,600. 15.6, 15.66, 15.66. Okay, it has crossed it. But because I'm going to add even a third pump. Okay, can even get up to 1,800 because. But let's see what the characteristics. I want to see how this where it will go. So I've just added a flow of 1,200 and this. All right, a flow of 1,200. When you get 1,200, the head is 14.057, 14.0, which is like 14.1. So it's too small with 1,200. With 1,200. With 1,000. So it's here. So it means that this is here. So this is going like this. Let's see. Down 1,400, 14.8. 1,400, 14.8 is almost here. Somewhere there. Okay, so that will 1,600, 15.6. 1,600, 15.6, somewhere there. So you get this as a system characteristics. Okay. Okay. You get that? So if you get your system, then if you get your system curve, this is our system curve, and this is for 2 pumps. Okay, so we're just going to look at where this intersects with that. Okay, that you get the flow and the head. So the flow will be, if you see that this is almost, you see around here, this is where you have the intersection. It's more than 1,200 and something. So this is, let's say 1,230. Okay, so flow Q is Q there for the 2 pumps is 1,230. This is liter per minute. Okay, which you can see convert to meter cube per second by just dividing by 1,000. That is 1,230 1000 divided by 60. Okay. So 0.0205 meter cube per second. 205 meter cube. So now that's Q. What about the head? The operating head here. So we're looking at this. You trace this. Okay. You trace this. This is about 14 point something. All right. So we can say that is about 14.15. So 14.15. Then efficiency. Can you see now that this is what is it? This is at this point the efficiency curve does not cut that. So what you do, because you have two pumps pumping, so you want to get efficiency, you look for the efficiency of one of the pumps, because there are two of them contributing to give this operating flow of 1,230. So that means the operating flow for one pump will be the flow that you have gotten divided by 2. So when you divide by 2, it comes within here, where you can match it with the efficiency curve. Okay. So in other words, I'm going to take this flow. I'm going to take the flow 1230 divided by 2, just to see how much will be the contributing flow for that operating point, and I'll use that to get the efficiency. 1230 divided by 2, we get about 615. 615. Okay, liter per minute. So I'm just going to look for 615. This is 600. 615. 600. This is 700. So 10. Okay. So I need to trace that. Trace this. This is 650 half. 615 is almost near there of 600, but you must trace it up. You trace it up to see where it cuts the efficiency. If you see, this efficiency is at 70 something, it's not up to 80. All right? And it's almost more than half of this. So if you take here, that is half, more than half of that. All right, you should be able to get 77% if you are using a nice graph. Okay, this is 70, this is 80. You should be able to get about 77%. So from there, our efficiency too is 77%. Now, once you get that, then you can get now the power. What they say, we must calculate the quantity which we have gotten. Now we have gotten the efficiency. Now the power. Power with the same formula, rho GHQ over that. So rho is 1,000 times 9. I hope you are seeing this. You are seeing up to this point. So I'm going to have the power. Power is 1,000 times 9.81 rho GH. The H is the head, operating head, which is 14.15. Then the Q is, we're not using this. We're not using this as our Q. I just use it to get efficiency. So our Q for the 2 pumps is that, which is 0.0205. So efficiency is 77. So when you do that, you should be able to get 36.95. Is it? Yes, I don't know. This is 0.77, please. What I'm getting, it should be divided by, okay. You get 3695. 3695.6, which is 3.7 kilowatt. Okay. All right, 3.7 kilowatt. Did you get that? What time is it? This is time to pass. Let's see the 3 pumps. Look at 3 pumps. Okay, so for 3 pumps, I just need to include what is it? The flow for 3 pumps. All right, let me just put it here. I'm going to clean this. At least you know what is there. When you have 3 pumps, which means this flow times 3, 0. This one times 3, 600. This times 3, 1,200. This times 3, 1,800. This times 3, 2,400. This times 3, 3,000. Can just stop here. So we'll just plot. So I want to see, I'm plotting this against our head. Okay, this is the head for the pump. So 0, 18, 0, 18. Now 17.5. Where you have this 17.5, the flow shoots up to 3 times, which is 600. So 600 here. So is there? And then at 16.5, this is 16.5, this shoots up to 1,200. It's 1,200 for 16.5 for that. So you see where it's going? And then 14.5, this shoots to 1,800. This is 14.5. It shoots up to 1,800. Okay. At least I will not even continue because this has crossed that. So I'm going to draw this. Okay. So I've sketched that. This is actually, I don't know. This is a characteristic curve for the top. Across that here is your operating point, of which if you check the flow If you check the flow down here, you are going to get, it should be about something more than, this is, here is 150. Just want to check. My listening is skewed a little bit. Just want to going to give you about 1,500 and something. Okay, it's 1,500 and something as operating point. 1,550. So this is for 3 pumps now. So Q is 1,550 liter per meter cube, of which you can convert it to meter per sec per minute. You can convert it to meter cube. Well, per seconds. Okay, at least we have that Q. Let's look for the head for 3 pumps. So you just trace this. Okay, if you trace this, so for efficiency, we are going to say 1,550 over 3, just to see the contribution from 1 pump to meet up with that static head. 1,550 divided. We are going to take it up, all right, and see where it cuts across that. So you take this until it cuts the efficiency, which will be somewhere here, all right, maybe half of that. Okay. We get about 5197. 5197. 5.2 kilowatt. Wow. What time is, please tell me, what time is it? Check your time for me. It's your time to pass, right? Okay. Take your time and play back the video.